Okay. Welcome everyone. Everyone can hear me, Dr. Jamal.
Ahlan. Yeah, I can hear you.
Yeah, great. Thank you for your patience and your support. We really appreciate it. Excuse us for the technical issue that happened earlier. So we truly grateful that you could give us time out from your busy schedule to hear from you about your valuable experience today. And also, as you can tell, we are a startup community, so startup quantum computing club, and we highly appreciate your support and hope that we leverage this to further grow the community. So I believe that quantum hardware is in the core of quantum computing field. What I mean is that scaling up and advancing this technology mainly depend on the quantum hardware and how we build the architectures. So we all are excited to hear about this. So without further ado, I will hand over the mic to Amir, who will kick off the discussion.
Uh, Thank you, Sarah. Hi, Jamal. I'm glad that we had the
Hi.
chance to make this meeting. Um, so yeah, so let's first talk about your personal journey and inspiration. So can you, Jamal, tell us briefly about yourself and what inspired you to pursue a career in quantum computing, particularly in developing superconducting quantum systems?
Yes. Hi, Amir. Hi, Sarah, and to the rest of the audience that would watch this video. Um, I'm Jamal. Um, well, um, I mean, since I was a kid, I was really fascinated by physics, right? I mean, I'm pretty sure all of you are, since you're somewhere in engineering and now interested in quantum computing. Um, so I did my bachelor in Libya, University of Benghazi, in 2013. Um, after I finished my bachelor in electrical engineering, which was the closest thing that you can do to physics. You know, like from the Middle Eastern cultures, either you go like a doctor or an engineer. So I had to choose between these two.
Hard
So I did
truth.
yeah. So I did electrical engineering, which was fun. Um, and then I joined a research company for about 2 years. After that, I came to Canada here in 2016, where I did my master's in basically power engineering. I'm not sure if you're familiar with power systems engineering, but it's basically the electrical grid that uh, that we use to supply, like to to uh, to generate, transmit, and supply electricity. So I worked on optimizing the electrical power flow to minimize cost. And while I was in Waterloo, I came into contact then with IQC there, and I've seen what they're doing. Um, the amount of effort and resources that people are putting at that place. And also, like, to be honest with you, if I'm not motivated, I find it very hard to do my job. And for um, for power system engineering, the field seems to be what would you call like a saturated. So it's like there's nothing you could do that would have a real impact. I'm sure there's still lots can be done, but it's very different than when you talk about quantum computing, right? So so one of the groups there, or one of few of the groups there, work on superconducting circuits. And what made it more attractive for me is that this platform, superconducting quantum circuits, it's kind of interface between electrical engineering because it has lot to do with microwave engineering. material engineering, and as well as physics, quantum mechanics, and quantum computing. So yeah, so that's what I did actually. I started my PhD actually in microwave engineering with Professor Omar Ramahi. I'm not sure if you probably you could look him up. He's a brilliant professor in microwave engineering that works on um, developing devices for early detection of cancer, for example, or um, wireless power transmission. So it was interesting to start with him, but then um, I switched to EQSL, the Engineering Quantum System Lab, because he wasn't interested in doing quantum computing.
Maybe he
Uh,
didn't believe in it yet.
I think like for him after working, I don't know, like 20 years in microwave engineering, it's very hard to switch
Yeah,
kind of
yes, yes.
in a new field for him.
Okay, okay, Dr. Jamal. So about your PhD, so can you share your journey from academia, completing your PhD, to becoming a postdoctoral fellow, and how did your research interests evolve during this period?
Mhm. Yeah. Yeah. So to work in quantum computing in general, you have to cover um, a little bit of ground in terms of like quantum mechanics, physics, and also a little bit of advanced microwave engineering topics. So the first like a year or the first year, I would say, you would focus on courses to try to catch up with what you need to start your research in superconducting devices. So you generally need to take courses that like cover what you really need in the specific research that you do. So like microwave engineering, um, there are like courses about quantum computing devices. So how you would implement quantum computing, for example, superconducting circuits. Um, there's also courses about quantum information. So it's like an abstract way of understanding quantum information processing. Um, and then generally you start by exploring topics and discussion with your supervisor, what can be an interesting topic to do, to, to work on. And so I think what's important to understand is that for your PhD, it's not, you don't need to solve the world's problem. A PhD is basically in general, okay? In general, it's it's a degree of like developing your critical thinking, like acquiring the knowledge and research skills. So it really takes some time to develop that. Would be nice to have an interesting problem to work on, which is generally what you would have if you work in quantum computing. Um, assuming you guys are interested in quantum computing. Um, so it, what I wanted to say. Yeah, so generally it takes like a collaboration with the group members. So it's really for experimental too. There's a lot of like a hands-on experience that you need to catch up with. And usually that means that you have mentors, like the more senior students or other postdoctorals that help you learn how to use the simulation tools, how to work in the clean room facility for fabrication, how to conduct the experiments. So I had a chance to work with very nice senior students there and learn a lot from them. And along that path, you help in their projects, but also you start working on your own project, right? And it generally it's like a an open-ended question. What would be your PhD thesis? Because some problems you might be lucky you get your results and you finalize the project um, faster. Some projects you get very unlucky and things could go wrong, and that could delay your project. Um, for example, in my PhD, um, probably the cryogenic fridge, right? This is the fridge that we use to place the device to cool it down. So it broke twice in one of
Oh,
my experiments, and that delayed like 1 year basically,
wow.
which is also yeah. So it kind of sucks for your own project, but it's part of the experience because what we had to do during that time is to fix the fridge. So you actually you develop experience in dealing with the fridge, how you can maintain it, how you can fix it. So for being an experimental, this is basically like a 80% overhead in terms of the experiment. So like 80% working on the experiment setup, working on the fridge, maybe fixing, maintaining, and then 20% doing your own experiment. It comes like a one package.
Yes.
So it really depends. For theory, I think is probably much less overhead. Um, yeah, in my PhD, I did three main projects. Um, and they all like revolve around what's called quantum simulation, analog quantum simulations. So we build circuits, quantum circuits that can mimic dynamics of some physics problem. So you look at theorists who worked on a model that described like superconductivity in 1D, and then we ask the question, can we make a device that actually showed the same dynamics uh, as that model, as that theoretical model, and we can show that okay, this theoretical model actually have validity to it because experimentally we have a device that have the same Hamiltonian or same like dynamics, and now we can show that the results actually matches with the theoretical model. So I worked on three different projects um, that shows three different theoretical models that demonstrate that they can be replicated and validated. Um, After I finished my PhD, um, the postdoc is generally comes at a transitional period. So like you finalize your thesis, if you have like some papers you haven't finished, you can finish them at the same time you start like exploring your options. What do you want to do after your PhD? Which you have mainly two paths, right? So like you want to do academia or you want to do industry. Um, at the same time, in this group we had an interesting project that we could extend on during my postdoc, and the idea was to make a bigger like a quantum processor. So I fabricated a device with 6 qubits, and that's that becomes like as a platform also for analog quantum simulation. So the idea is that now the future students can come and use that device and then like build other theoretical models using that device and try to study them. Um, so I jumped to the industry versus academia, right? So unfortunately, for like, I don't want to discourage you from the academic uh, path, but it really depends on what you want to do. Academics, you have like your freedom of research in terms of what you want to do. Your freedom of time also. It's very flexible to work like as a professor in uh, in a university. But for in general, the number of academic positions are very, very small. And Right now, you would need to do like a 3 to 4 years of postdoctoral after your PhD before you get a chance to become professor at a good university. Um, the other path is industry, which is also, I mean, for quantum computing is very interesting because in industry also all what they work on is research. So uh, instead of working in academia with your own group, now you would work in a larger group, like 50, 100 people that are working on developing a quantum computer. You would just be like working on a specific problem and improving it. And as um, as Sarah pointed out, now for the hardware part of superconducting quantum computing, the uh, the main goal is basically to work on engineering the device, making it improving the gate fidelities. That's just like the reducing the error rate when you implement the quantum gates, or when you measure the qubits, or when you prepare the qubit states before that. This becomes harder as you increase the number of qubits, but in general, this is the main engineering problems that are now people who are working on superconducting quantum computing um, are dealing with. So right now, I'm actually like leaving my postdoctoral by the end of uh, next month, and hopefully, joining Google in February.
That is great news. For the best for you.
Congrats, congrats.
Well, I hope I answered your question.
Yeah, actually, you answer some of our next questions also. So now talking about the superconducting quantum devices and your experience at the EQSL. Uh, so for those who hear about it for the first time, could you briefly explain what the superconducting qubits are?
Sure, yeah. So maybe we can start, but what is a qubit, right?
No,
It's a unit of a quantum. It's a unit of quantum information, as like it's the quantum version of a bit. It's the most fundamental information unit of being a 0 or 1 that allows for two possible states. The qubit is basically it's a short for a quantum bit. That's also the fundamental unit of information that you can store. And a superconducting qubit, it's a hardware uh, device or an element that can be used to store a qubit of information. For superconducting qubits, we basically use electrical resonators or electromagnetic resonators, basically, or LC circuit. Now, because the LC circuit has what's called like an infinite Hilbert space, which means it has infinite number of states that it can be at energy levels. So you would need to make it a nonlinear LC resonator. So why nonlinear? Because when you load the information in the form of a electromagnetic photon, you can only load one photon. The second photon you need to add to a nonlinear LC resonator has to be at different frequency. So it acts like some sort of a selective LC resonator that can only observe one photon. And now the state of the information is basically, if you have a photon in that LC resonator, it's at 0 state. If you have So if you don't have a photon, it's a zero state. If you have a photon, one single photon, it's a one state. So how can you make the LC resonator nonlinear is by adding the well-known Josephson junction instead of an inductor. So an LC resonator has a capacitor and an inductor. Now you could replace the inductor and with a Josephson junction. A Josephson junction is not a magnetic. It's not an element that stores magnetic field per se, but it's an element that stores energy and what's called the phase of a wave function. But you can think of it as a nonlinear inductor anyway. So this is how you add nonlinearity to the qubit. I'm hoping I answered the question. Sorry.
Yeah, well, I always hear
Yeah.
that how is the superconducting qubit is basically an artificial atom. So I think that's also a nice way to put it, because first time I heard about it, I could kind of imagine it a little more better. But yeah, yes, it was.
Yeah, I think it's very common that people say it's an artificial atom. Some people also don't like to call it a nonlinear resonator because it's not really a nonlinear resonator. This is the closest that you can say that you can use to describe it.
Thank you, Dr. Jamal. So you've actually answered a part of this question, but let's say for more specifically, could you describe your experience working at the Engineering Quantum System Lab, the EQSL? And so what's the lab's primary focus, and how does your work contributes in the overall goals?
Yeah, it's okay, let me think about it to answer it in the next one.
Take your time.
Yeah, I mean, overall, I think it was very good experience. I can tell you why. And when you work in experimental groups and superconducting, usually these groups can take different approaches. There are groups that ask students to specialize in one thing. So, and if you could do like theory work part of the theory part, or you can work on fabrication. You can choose to do experiments. But generally, you just focus on one of those. The other type of groups, which is EQSL, is that you have to do everything from scratch. You get help from the senior students, but you get a chance to develop your skills and knowledge in working on the theory, working on the device design, on fabrication and experiments, which can take much more harder than just working in one of them. But I think for a PhD, it's very important to be to have a well-rounded experience in all of these topics. For two reasons. The first reason, if you want to go to academia or you want to lead groups, you need experience to understand these, because people that will work with you or under your supervision will be working at these different parts, right? So you'd have if you want to work in a bigger project, some people will work in theory, some people work in experiments or fabrication. It's very important to have experience in all of these. Or if you want to do your own, or if you want to become a professor and have your own group. The other important thing is also if you go to industry, you have more options in terms of the jobs that you can apply for and the jobs that you can work on. You would be you would be competing with other people who have more a specialized experience, but in general you have part of that experience anyway. And in addition to the in addition to your experience in the other topics as well. The lab primary focus you asked is analog quantum simulations, like I mentioned, and as well as quantum optics. So it's the same use of devices, but it's more of, let's say, generating entangled photons. So like you generate a continuous stream of entangled photons that can be used for quantum or other quantum applications like quantum sensors or quantum radar. Using the same, typically the same devices. Yeah. Maybe what would you need to get a chance to work in AQSL? I would say some electrical engineering background because it's mainly focused on the experimental part. Yeah, a little bit basics of quantum mechanics is also would be helpful, but it's not crucial, I would say.
Thank you. So, talking about the challenges, what are the biggest hardware challenges that you faced in designing superconducting quantum devices, and how do you overcome them?
Okay. I think since we're not talking too technical, I'll try to touch on that. So okay. I think there's the most challenging part is to make the device that would have the same physics as your design, as your circuit. So there are two levels of like the device design. You could think about it in terms of writing the mathematical description of the device, like having a capacitor and an inductor and a bunch of those that are coupled with the capacitors or inductors, and you can easily write the mathematical description. You can run Python code that give you the results, and then you optimize that. But then once you want to translate this into an actual device, right? So you would need actual physical layout of what the qubit looks like, what the coupling, the qubit capacitance looks like, and the coupling between the qubits, making the device, the actual physical device description as close as possible to the mathematical description is the most challenging. Now, there's these simulation tools that you can use, like HFSS. This is basically like electromagnetic field simulations, and other also simulation tools. I can mention them, Keysight ADS or Q3D. These can help understanding the physical qubit, the physical device, and you can from there optimize it. Now these simulations tools also don't take into account superconductivity. So it's just like I use normal metals when you do your electromagnetic simulations, but the actual device is superconducting. And superconducting materials add more physics to the most important part is what's called kinetic inductance, because now electrons, when they move across the superconducting material, they don't experience resistance. Because of that, the actual kinetic energy of these electrons also comes into the picture as effective inductance. So this also needs to be taken into account. So it's basically doing that and doing measurements and then taking the data back to the design as a feedback. So it takes like 2, 3 iterations between design and experiment before you have the device that you're designing. This is the challenging part in designing quantum devices. Yeah, at the small scale, of course.
Oh, thank you. So, uh, so what are some of best practices in controlling and measuring superconducting devices to ensure precision in quantum experiments?
Um,
I believe
uh,
it's hard to describe without slides and stuff.
yeah.
I can understand. I can completely
Sorry.
understand. I see that. Okay, I need the slides. It's okay.
I'm also,
Try not to
it's
go
very,
too
Take your time.
technical.
it's very generic question also. It's very, I don't know how to answer it. But okay, let me try to show you something.
Okay.
Um, okay, can you enable the sharing option?
I don't know if this works. Can you please try again?
No, no, it's not working.
Okay, I'm trying to.
Yeah, Khalid, I just saw Khalid's email, Khalid's message. That's
Yeah,
totally true.
right. I noticed that you didn't notice it from before. Yes. Okay. Can you please try again? Maybe because I should have a message, like I should receive a message when you try to share the screen.
Yeah, that's what I expected, but it just
Oh, okay,
says
okay. I think this should work. Okay, great. I think this should work.
okay. Yeah,
Yeah.
now it works. Um, so yeah, if this is maybe the question is what to use in the experiment to control the qubits, it's usually like I mentioned, this microwave instruments. So and usually they come from these instruments originally come from usually communication engineering people. So some of the instruments here are literally what research labs that used for like 3G network research like a decade ago. Do you see my screen? Yeah, so for like a qubit control, it's usually a what's called an AWG, so it's an arbitrary wave generator. You basically draw a pulse shape digitally on the computer, and then at a certain what's called like intermediate frequency. This is basically the frequency. The higher the frequency, the more precise is your digital pulse, because you can think of it in terms of like sampling sampling an arbitrary like mathematical pulse with that intermediate frequency, and then you have these what's called like digital to analog converters. So these are like electronic boards that have very advanced switching, and they create the pulse digitally, uh, from digital to like actual voltage at the output. And then we use what's called IQ mixing. These are microwave mixers that takes the pulse at like a few megahertz frequency to gigahertz frequencies where the qubits usually at the qubits and the resonators. And then could use radio frequency amplifiers to increase the strength of the pulse, or the strength of the control signal. Because what you have along inside the fridge is what's called attenuators. So these attenuators reduce the input power at a lower and then produces an output power. It's very like a passive elements. And the idea why you have like all of these are attenuators. The idea of why you have attenuators is, in addition to your signal, you have a background noise, and you want to reduce the noise as much as possible. So you create a very strong signal, and then as it travels down the fridge, it's attenuated, but also the noise also is attenuated. So you have a better signal at the device. And now you can use the same setup for control. That's basically the qubit control, the gate control, the readout pulse, everything. And then at the output, you use what's called a circulator. So a circulator it's a directional device. Maybe this is the best I can say. It's basically, you see these arrows here, they basically indicate that if a signal comes this way, it like takes this half a circle and then moves this way. But if a signal comes back down here, it goes half, like a quarter of a circle, and goes here. It doesn't go back to so basically it allows a signal to go from here to there, to the output, but any noise signal coming from the output down here does not pass to the device. So it's an isolator. It isolates the device. It allows a signal to go only in one direction. Usually also people have what's called like a TUPA, or a Josephson junction amplifier. The idea of these amplifiers, they work at 10 millikelvin, so they have a minimal noise, as opposed to like the standard electronic amplifiers that do not work at 10 millikelvin at this very cold temperature. The best amplifier that works at cold temperature is what's called HEMT, like high electron mobility transistor. It works at 3 Kelvin, but this is still much higher for what's called noise or temperature compared to the output signal. And then at the output, we use an analog to digital converters at the gigahertz. So these are to measure the readout signal. So like you create a readout signal here, and then you measure it. You measure it at the output, and then you digitize it. Okay, I hope I gave as much as I can for that question.
Thank you for your explanation. It's actually nice to see some of what we did the study at the university, implemented um, here in the slides. Thank you again. So now talking about the future advancements and impact. So in your opinion, what major breakthroughs in quantum hardware do you foresee in the next 5 years? Uh, and how will they impact this field?
Um, yeah, I don't think I know the answer to that question, but I can tell you what I think. So, so the main let's think about the main limitation for the qubit, for the superconducting qubit. The main limitation is one of them is loss, what's called loss or noise. So loss basically is these other these um, contaminations near the device or near the qubit that observe the photon in the qubit. So the idea is that if when you put a photon in the qubit, you want it to stay there. You don't want to lose it. But because of the contamination near the qubit, so the qubit is basically what is a superconducting device, right? It's what's called a wafer. So it's like a cylindrical thing here that's very thin, about like a millimeter, made of silicon, with as less pure impurities as possible. And then you coat it with the aluminum film, very, very thin aluminum film, like a 300 nanometers. And then you draw your qubit. You draw your circuit. For example, the dark spots are here, the silicon background, and then uh, the brighter parts here are aluminum, right? So you basically you draw your circuits on the aluminum, but in this fabrication process, you introduce contaminations, which is maybe let me mitigation. I'm pretty sure this. Yeah. So you see here, this gray area here is silicon, and this thing, the brighter gray here is aluminum. But in fabrication, you have contaminations between the aluminum and the silicon in this like a blue layer, and it's usually silicon oxide, or you have this um, aluminum oxide and silicon oxide, and also on top of the aluminum, and on the silicon here at the and between the air and the silicon. So these contaminations observe the photon that you load in the qubit. That what limit what's called the qubit life, is the lifetime of the qubit before it dies or before the photon is observed by one of these contaminations. So I think a major part, a major important breakthrough is probably not a breakthrough, but like a continuous advancement, is to improve and by reducing these contaminations to have a higher qubit lifetime. For example, in this paper, they basically improved the qubit lifetime by making the aluminum thicker. So usually people use like 100 nanometer aluminum film. Now in this paper, they use from 300 to 500 nanometer. So these type of improvements, engineering improvements, I think would be helpful. Some groups or some researchers also claim that there are special types of qubits, for example, what's called a 0-pi qubit. So these are more complicated qubits that require very fine engineering of inductors and capacitors to make the qubit um, robust or insensitive or not sensitive to these type of contaminations. My guess is that these qubits are too complicated to use to scale up. I believe like the simpler architecture like this one, right? It's just like a capacitor and a junction, but improving the losses would make it better. Now, for example, Google have single qubits of like a 300 microsecond. But then when they add more qubits, like 100 or 200 qubits, or I mean even 50 qubits in their chips, the qubit lifetime goes down to 50 microseconds. Because now you have the complexity of having 50 qubits, and each qubit have its own like control lines and its own resonators, um, and it's coupling not only to these qubits but also to other qubits in the circuit. And this make it more of like a microwave engineering problem. So the idea is that when you apply like a microwave signals, you want the microwave signal to go to the qubit, to the target qubit, and not go to the other qubits, so that you don't affect the performance of the other qubits. Now, this also does not necessarily require a breakthrough, because the problems are known, and generally the way to deal with these problems is also known. But you need more of like an engineering and smart physical layout engineering. Well, other than that, what is it? Yeah, maybe a breakthrough would be in terms of the type of material people use and instead of aluminum. So, for example, there are groups from Princeton that use tantalum instead of aluminum. They could create qubits with 500 microseconds lifetime. But then now people reach that with just aluminum, but making the aluminum thicker. So it's kind of very vague area as what you would need to do to make things work. But I think at this stage, it's a lot of engineering. It's a lot of engineering work. And yeah.
Thank you, Dr. Jamal. So, last but not least, what advice would you give to students like us who are focusing on the hardware aspects of quantum computing? And if there's any book or paper recommendations. So yeah.
Yeah. No, I can certainly. So what is it? There are a few review papers. There's a book by my supervisor that was published like a few months ago, I think. But it's not open source. There's a book by Steve Gervin. I think it's very nice, very, very nice introductory book or notes. I can probably make a list of these references that you can use. There's a review paper by Alexander Blaze, but it's much more involved theoretically and a little bit more advanced. So even if you want to work on hardware, like I mentioned, like a microwave engineering, so that like a book by Bozar. Did you guys study like microwave engineering? I don't know.
It's actually so since it's hardware, I would like it's nice actually.
Yeah, so there's a book by Bozar, Microwave Engineering. You would need to study quantum mechanics, like the basics of quantum mechanics. There's a book by It's a well-known book by what's his name? I forgot his name. I'll send it to you. It's an undergrad level book. There's another. So quantum mechanics, there are two approaches to studying quantum mechanics. Griffith, yeah, Griffith. Um, there's that book for undergrad that usually like focus on using mathematical functions, but there's another book that uses matrices or linear algebra to study quantum mechanics, and this is more relevant to quantum computing and also for the hardware part. There are summer schools by IBM I think they're available on YouTube. They're very, very important. I still go to them when I want to refresh or look at certain problems. They have their own like open source code. It's called Qiskit Metal, which you could use to play with yeah, it's very, very nice. It's all the groups, like even in Amazon and Google and IBM, they more or less use the same type of software to design to design their devices. What else? Yeah, for experiment and fabrication, I don't know of a book that talks about all of these. It's generally like a hands-on experience. But but for you to go like to have an opportunity at one of these groups, you don't need that experience. I don't think anyone expects you to have a fabrication experience if you're applying like for a master's or a PhD student. Yeah, let's say if you want to apply for a master's or a PhD, yeah, as I mentioned, like microwave engineering background, quantum mechanics background, Qiskit Metal, I think would be very, very good skill to have if you apply to one of these groups. And what else? Yeah, I think these are pretty much are the topics that I would study. Yeah.
So, there's any advice you can give us, general advice or something for our future career or journey?
I don't know, make use of your time.
Someone told us don't get into quantum computing. It's a lot, but
Yeah, well, it's for hardware, maybe that advice is not it's not very important. Like the type of expertise that you will have, you can generally like transform to other fields basically. Now, quantum computing is very risky. Like it's still not very clear if it's gonna work, right? So like if, for example, one of the famous applications for quantum computing is encryption, right? The ability to factorize numbers. And if you want to factorize like 21, the number 21, if you want to find if you want to factorize it, you need like 1,000 physical qubits. You can imagine that. So it's still way ahead of it's still way ahead of us before we can get to something very useful. There's also not there's not a mathematical proof that quantum computing or like a quantum machine learning will be fundamentally better than classical computer.
no clear quantum advantage.
Yes, there's not a mathematical there's not a mathematical proof, at least for quantum like machine learning and quantum algorithms. There's no proof that tells you that there will not be like some smart quantum science, like computer scientist that will come up with an efficient algorithm to solve a problem classically as fast as a quantum computer. But look, I think these are open questions that they will not be answered until we have an actual quantum computer, if we do have in the future. So it's risky, but it's also rewarding uh, at the same time. I would want to be careful about what I do in the quantum computing realm in terms of like if you want to do your PhD. Because like I don't know, like most of the other fields as well, eh, I don't know, like having a PhD in other fields also is not, it does not qualify you to have like a way, um, like a bigger opportunity in terms of like jobs or anything. It's just for a PhD, it's not something that you would seek if you're looking for like a financial benefit, for example.
It's
Uh,
actually hesitations. I mean, there is in the hardware field. I mean, there's many paths that a student can go with. Most students, I believe, that they just focus on one path or one field, and like you said, it's risky in the quantum field. So I think, in my opinion, I think uh, to be general, not go deep in the quantum field. Maybe it's the right choice, or I don't know,
yeah,
but
like
that's what I believe.
yeah, if you mean like maybe superconducting will not work and like other platforms
Yes,
like trapped ions, yeah, it's possible. It's possible. Like no one can tell you that which platform will work. Superconducting generally is for sure like one of the leading platforms, but it's not it's still not clear which platform will work eventually.
I mean, if Dr. Jamil now is in our shoes today, uh, you will do the same. I mean, be general in overall, yeah.
I think I will do the same. Yes. I feel like the superconducting the experience I had is was interesting and it's not limiting me in terms of where I would go in my career like if like a finding a good job for example. I think the experience you would get like from fabrication, from microwave engineering and experiments can allow you to work in other fields, not necessarily quantum computing. Like worst case scenario, if no company or no university is interested in doing superconducting, for example, anymore. Yeah.
But there is something recently, and you mentioned it, like about cascade metal, for example. I think also the open quantum hardware that allows like people to not experimentally fabricate and use quantum hardware. They allow students to work, but at the same time, if we go and look and search about it, it's not actually open source. Like for instance, Qiskit Metal does work with HFSS, and but ANSYS itself is not an open source. So when
Not
you
an
come
open
to the simulation part, you're gonna be surprised. Oh, I need to be part of a company, or I need to be part of a bigger institutions in order to be able to even access this. So this is actually disappointing because if someone wants to make sure, okay, I want to take part in the quantum computing PhD programs. So I want to work with quantum hardware without me like formally do it. So I will use the open quantum hardware, but actually you can't do this because I've tried to
Yeah.
do it, and it's like at some point you need to be part of something in order to have this license to work with. I don't know if I'm wrong, but like that's from my little experience.
Yeah, HFSS license is very expensive. It's true. Like I'm not sure, like you can try to see as a student if you can get access to it, but there are other ways that you can get access to it. Like I can't mention maybe online, but you
Yes.
know, all other groups, all many other students get access to HFSS in one way or another. It's unfortunate that the price is very expensive, especially like when you compare it maybe not to the US or Canada, but to other parts of the world, right? I don't know what's the license is, but it's probably like $1,000 or $500 a year. I don't know. That's my guess. Um, but yeah, like having access to HFSS is very like a crucial if you want to do quantum computing hardware. There's another open source software by Amazon, but I haven't used it. It's called Palace. Maybe check it out. But I haven't used it. Maybe I can also share the link.
Great. Thank you. Thank you. I'll check it out. We all should actually. So, thank you so much for your time, Dr. Jamal. It was nice discussion, an hour of really nice talk. And
Yeah,
thank you, Amin, for
yeah, it's my pleasure talking to you guys.
Thank you.
There is actually before we end this, uh, it says ANSYS Electronics desktop student free software
I do
download.
have it as well, but it is not supported by Cascade Metal. It's you
Oh,
can't connect.
really?
Yeah, so there's
It doesn't.
the COM, there's the I think it's a component object, and you cannot connect it. So basically, it's like it's
I see.
limited version, so you cannot simulate the. But I'll see what I can do.
I see. I see.
Okay. Thank you, sir. But before we finish, I have a question related to the topics that Sarah said right now. Do you believe that a student living in Palestine or somewhere, you know, like a lot of students doesn't have access to real hardware quantum? So, do you believe that a student living in Palestine can have similar experience to a student living in somewhere where he can try to access a hardware, a real quantum hardware, or do you believe that it's much harder for students who are trying to do some research about these topics without access? What do you
Mhm.
think about this part?
So, okay, let me answer it positively. I
I hope.
think I think you can head start in terms of like reading and like working on designs and like developing some basic skills that you would need. But ultimately, for like a hardware design and experiment, there there is the crucial part, which is um, like a hands-on experience, the discussion with the supervisor, the the resources. These are not available not only like in Palestine, but in most of the world. Like for example, in Canada, there are like 4 or 5 experimental groups, right? In the US, there's much more. But this experimental superconducting or hardware design is you need to be part of a experience group to be able to contribute, I think. But you can always build skills that is important that then make you a good candidate when you apply for like for a student position. Now, I think what can you do? Hmm, I'm trying to think what can you do to make your like a CV maybe or like a resume much more attractive. Um, yeah, maybe looking at some of the designs, replicate the results, the simulations, the analysis, um, would be very helpful. Um, oh, I am not sure in terms of the what is it? I have met lots of Palestinian students here, but I'm not sure how hard it is to for you to travel. That's that part of the question. Maybe I don't know what the answer to that question. Um, but there are lots of opportunities, I would say. Yes. So
Yes.
so do you mind telling me like what's your background generally? Are you doing computer engineering or like electrical and computer engineering or uh, what's
Well,
exactly are you
yeah,
studying?
I'm a computer engineering fresh graduate. I worked on as a hardware engineer. I'm trying to get into um, physical physical design right now, but I'm most interested in quantum computing because of its potential. So I was thinking that can I really get a real hands-on experience without without having access to quantum hardware. So I understand from your answer that I couldn't really. I have to travel in order to achieve that. Am I understanding this correctly?
Yeah, yeah, yeah. Now
Okay.
um this is the hardware like a design part. The there are things you can have access to maybe. It's like IBM quantum computer.
Hmm.
I think they provide like a free time to use their quantum computer, but it's not. I don't know if it contributes to your hardware design experience. Maybe it's nice to play with it, but it's not necessarily like important. It's not necessarily crucial for hardware engineering. But the good thing is that if you require like a starting position, you don't need to have that experience if you want to do like a master's, especially or a PhD, right? If you want to look for a job directly, I can tell you it's very hard to find a job just with a bachelor degree or like also like it's hard to get a job in with a master's degree in quantum computing
Okay. Thank you, sir.
because it's mainly like a research. It's not impossible. Like two of my friends from the group actually are working as quantum engineers of masters, but they were more or less lucky. Like at the time they were looking for jobs, they were openings that required like a master's students. But if you look at the job openings, they're generally ask for PhD graduates. It's just the nature of the research.
Oh, absolutely. Thanks you for the great answers. and thank you for giving us the time. Thank you.
Yeah, sure.
I think I will start encourage more students from electrical engineering background to join us because we're mostly physics and computer engineering, and we have only two students from electrical engineering
Electric.
background. So there's gonna be like we need to tell them like, guys, look. So thank you again, and we hope maybe in the
Sure.
future to have more technical discussions or things like that. And I hope that you will see us like grow the community in a good way and learn from your experience. Hopefully,
Yeah, all the best. Like if you need any help, I can do uh uh I hopefully can do the best I can do for to help you. I will send you the references. I can give you a technical talk. Now, I think what I would give is generally available on YouTube from much better people
yes, yes.
than I am, like actual professors like Alexander Please or other professors. But you're all like always welcome to reach out if you're interested in a specific thing you would like to chat about. Um,
Great, great.
I can connect you to other people also if you're interested to hear from them. I have a friend here who finished his master's also. Maybe you can connect you with them if you would like to hear from his work. He's more theoretical, working on the theoretical part of quantum computing.
Yes, that would be great. Maybe,
Yeah,
but a little later, when students are also like more familiar with the theoretical part, and then like starting the actual design and stuff. Uh, Thank you, everyone, and thank you, Amir, and hope to see you in future speaking workshops, hopefully.
hopefully, yeah. Thank you.
Thank you.
Okay,
Bye.
bye. Good luck.
Bye.
Thank you.
Thank you.